Hello students, this is Sudhanshu Sarkar, Assistant Professor, Department of Electrical Engineering, Narula Institute of Technology. So it is electrical circuit and network. So already I have uploaded few lectures on online mode, and you know that in this series I'm just solving the AC circuits, resonance, okay, series RLC circuit. So this is the topic for this uh, series of lecture. So now here I think all of you have the idea about the lesson plan of this electrical circuit and network. So here in this lesson plan I have to cover three unit 2, 3 and 4. In unit 2 it's a single phase AC circuit and resonance. Now under this there is some topic of study of J operator, the concept of complex impedance, so like this, and then a parallel resonance, series resonance, problem, comparison, series and parallel resonance. These are the topics for unit 2. Now in unit 3 there are some principles of circuit, AC and DC circuits, both we have to solve here. And unit 4 it's like networks theorem, so different types of networks theorem is there, superposition, Thevenin's, Norton's, maximum power transfer theorem, like this. Now today, this is the second part, you can say, from the last lecture. So in last lecture I discussed on the series RLC resonance, RLC series circuit resonance, and now today I'm going to show you two problem that which is related with series resonance. So it's a problem solution lecture, problem and its solution. I will show you that how to solve the problem related with this specific topic. So here in this lecture I consider two very simple problem, because this is the very beginning of your building up ability on resonance circuit. So for that reason I just consider a very simple circuit. Later on I will consider the complex one, and then it will be more then we will be able to solve the difficult problems. Now the example number 1, here I consider a series resonance network consisting of a resistor of 30 ohms, capacitor of 2 microfarad. Okay, so note down this all these given values. The resistors of 30 ohm and the capacitor of 2 microfarad, and an inductor of 20 millihenry is connected across the sinusoidal supply voltage. This is the sinusoidal supply voltage is given 9 volt, which has a constant output of 9 volt. Yes, that is also given in the figure. All frequencies, at all frequencies. Okay, no problem. Calculate. So what we have to calculate? Number 1, the resonant frequency. Number 2, current at the resonance. Number 3, the voltage across the inductor. Number 4, capacitor at resonance. Now the quality factor and the bandwidth of the circuit also sketch the corresponding current waveform, all the frequencies. So here the problem is given, R is 30 ohms, that is given in the problem. L is 20 millihenry, C is 2 microfarad. The AC supply voltage is V equals to 9 volts. The current which is flowing through the circuit, that is I. So this is the problem we have to solve. Okay, so it's a very basic problem. So first one, we have to calculate the resonance frequency. Now think on it. Think about the last lecture. So I derive all the equation related with series RLC circuit, series RLC resonance circuit. So here the resonance frequency is F You already know that the equation of the series resonance circuit is FR. If we consider the resonant frequency is FR, then we already know the equation of the series resonance frequency, that is 1 by 2 pi root over LC. That part is proved, also proved in the last lecture. So please go through that one, then solve this type of problem. Try to understand this type of examples. So here FR equals to 1 by 2 pi root over LC. So 1 by 2 pi L is given, that is 2 millihenry. C is also given, that is 2 microfarad. Am I right? Go to the last slide. Yes, 2 millihenry L and C is 2 microfarad. So we convert it 2 millihenry to the henry 0.02 and microfarad to farad. That means we need to multiply with 10 to the minus 6. So here we put both the value. This is the value of the L, which is given in the problem. This is the value of the C. The value of the L, which is given in the problem, that is 2 millihenry. So we convert it 2 millihenry to henry, that will be 0.02, and C value was given, that is 2 microfarad. So from microfarad to farad, we need to multiply with 10 to the power minus 6. So we put all this value in this equation, and then using simple calculation, the value of the frequency, resonant frequency, here in this case, this is 796 hertz. After calculation, we find it 796 hertz. Okay, so it's simple. Just remember the formula, and if you know the basics, you can also develop the formula. You can derive the formula also. No problem with this. Now the next one, circuit current at resonance. So the circuit current at resonance, if it is Im, if we consider the current circuit current of resonance is Im, then I equals to V by R from Ohm's law. You all know this. It is equals to 9 by 30. So the voltage given, that is 9, and the resistance is given in the circuit, that is 30 ohms. The voltage was 9 volt and the resistance is 30 ohms. So just put these two value, 9 by 30. So the equation is 0.3 ampere or 300 milliampere. So this is a simple Ohm's law. Applying Ohm's law, we can find the circuit current at resonance. Now the next one, inductive reactance as resonance. You know that inductive reactance, we represent inductive reactance with XL. So several time I explain about XL. So the equation of XL is omega L. You all know that XL equals to omega into L, and omega is the angular frequency, that is 2 pi f into L. So here 2 pi, 2 into 3.14 pi, you know the value, 3.14 or 22 by 7. And the f, 2 pi f, if we find it in the last slide about the f, 1 by 2 pi root over LC. So from there, we find the value is 796. And finally, the value of the L is 2 millihenry. That means we have to convert it to Henry, so 0.2. So this is the value we get from the problem, and then after calculating, after multiplying all the values, we will get it. The value will be 100 ohms. So XL is 100 ohms. Now the next part of the problem, that we have to find the voltage across the inductor and the capacitor. Yes, voltage across the inductor for series RLC circuit is VL, voltage across the capacitor is VC. So here for resonance circuit VL equals to VC. Then you know that VL equals to I into XL. This is the equation of voltage across the inductive reactance. So I is 300 milliampere. Yes, so we already find I in number 2, that is I is 300 milliampere. So just put it here, and then XL value is 100 ohms. XL is already calculated in third part. Then just put these two, and finally the value of VL, this is 300 milliampere into 100 ohms. So calculating, will get the value is VL will be equals to 30 volts. Now you need to remember some notes that the supply voltage may be only 9 volts, but at resonance the reactive voltage across the capacitor VC and the inductor VL are 30 volts peak. The supply voltage may be only 9 volt, but at resonance the reactive voltages across the capacitor VC and the inductor and VL are 30 volts peak. Now try to remember the equation of the quality factor. So quality factor is the ratio, we represent quality factor by Q. So it's the ratio between inductive reactance and the resistance of the circuit. So inductive reactance is XL and resistance is R. You all know this, so I don't need to clarify it again. So XL by R. XL is already calculated in the last slide. No, the second or third slide. That is 100 was the value of XL, and the resistance is given in the problem itself 30. So if we divide 100 by 30, so the value of the quality factor will be equals to 3.33. This will be unitless quantity because it's ohms by ohms, XL by R. No unit for quality factor. So in this way we can find the quality factor, and for this particular problem the value of the quality factor is 3.33. Now the bandwidth. So we represent bandwidth by BW. The bandwidth equals to FR by Q. FR is the resonant frequency. So we find the resonant frequency. The value was, can you remember the value? 796 hertz. And the quality factor Q value is just we calculate in the previous slide. So that is 3.33. So if we divide 796 by 3.33, the result will be 238 hertz. Okay, so in this fashion we can find, with the help of this equation, with the help of the resonant frequency and quality factor, you can find the bandwidth, because we know that the ratio between the resonant frequency and the quality factor is basically the bandwidth of the circuit, resonance circuit. So here the value is FR by Q, that is 796 by 3.33, that is equals to 238 hertz. Now the next one is the upper and lower. There's 3 dB frequency points, high frequency and low frequency. So FL, you know the equation, FL equals to, that is the low frequency equals to FR, resonant frequency, minus half into bandwidth. So the resonant frequency, this is the equation for low frequency, FR minus half bandwidth. So FR is 796, of bandwidth is 238. Okay, so 238, we just in the previous slide we find the bandwidth that already calculated for this particular circuit is 238. So it's a simple calculation, and finally the value will be 677 hertz. And the high frequency value is FR plus half into bandwidth. So this is the second equation for finding the high frequency. The low frequency there will be negative sign, and for high frequency the positive sign will be there. This is the resonant frequency plus half into bandwidth. So resonant frequency is 796 and half into 238. So calculating will get the high frequency is 915 hertz. So in this way we can find the value of the upper and lower frequency, that is respectively FH and FL. Now the current waveform. So here you can find the current waveform for this particular circuit. So now let's try to understand. So the high current pickup current is 300 milliampere minus 3 dB. It is 212 milliampere. Now the FL is 677 hertz. You calculate this FH high frequencies 915 hertz, and the resonant frequency is 796 hertz. So it's a current versus frequency curve. So the current waveform will be like this. So it will grow, and then 300 is the peak value, then again it will go down. So this will be the current waveform for the series resonance circuit, which is given in this problem. Now we are moving to the example number 2. So in example number 2, the problem which is given, a series circuit consists of a resistance of 4 ohms, an inductance of 500 millihenry, and a variable capacitance connected across a 100 volt 50 hertz supply. Calculate the capacitance required to produce a series resonance condition and the voltages generated across both the inductor and the capacitor at the point of resonance. So read it again for the clarity of the problem. A series circuit consists of a resistance of 4 ohms, inductance of 500 millihenry, the variable capacitance connected across a 100 volt 50 hertz supply. Calculate the capacitance required to produce a series resonance. We have to find the capacitance condition and the voltage generated across both the inductor and the capacitor at the point of resonance. So in resonance condition we have to find all these things, all the required value. Now you all know about the resonance frequency, that is FR. We just represent by FR the resonance frequency, and the equation um, um, XL is the inductive reactance equation. XL equals to 2 pi FL because XL equals to omega into L. So omega is 2 pi F, that is the angular frequency. And you know that 2 into pi, 2 pi into frequency is 50, and L is given here 0.5. 500 millihenry, that means 0.5 Henry. So simply putting the value 2 pi FL, 2 pi 2 into 22 by 7 or 3.14, and F is 50 hertz, L is 0.5. So calculating will get the value of the XL inductive reactance 1.57 157.1 ohms. Now at resonance we know that XL equals to XC. So when you can find XL, so you can easily say that the value of XC will be same, because this is the condition of resonance. The inductive reactance should be equals to the capacitive reactance. Okay. Now moving to the next part, find the capacitance C. Okay, so what is C? C is equals to 1 by 2 pi F into XC, because we know that X equals to 1 by 2 pi FC. So we can easily write, what do we know? We know that X equals to 1 by omega C. that means from this equation you can say that C equals to 1 by omega into xc. Okay. So 1 by omega, you all know that it is 2 pi f is omega into xc. So 1 by 2 into pi into f is the 50, and the value of xc, we just find it, value xc 157.1. 157.1. So just put it, and putting the value, simple calculation, you will find that the value of the capacitor is 20.3 microfarad. So in this way, we can find the value of the capacitance. Now, this is the voltage across the inductor and the capacitor VL. The voltage across the inductor and the capacitor VL, to finding, before that, first we have to find the supply current, that is IS, that is equals to V by R for Ohm's law. The voltage is given here is 100 volt and the resistance is R, so the current value will be 25 ampere. So at resonance, we know that VL equals to VC. So VL is nothing but I into XL, that is the voltage drop across the inductor. So voltage drop across the inductor, the equation is VL equals to I into XL. So I is 25 and XL is 157.1. So then multiply 25 into 157.1, thus VL equals to, the value of VL will be equals to 3927.5 volts. That means you can say 3.9 kV, or VC equals to 3000. Same value will be there for both the cases. So in this way, we can find the voltage across the inductor and voltage across the capacitor. Now the next part for this lecture is the series resonance summary. Let me share the summary of series resonance. You may have noticed that during the analysis of series resonance circuit, in this tutorial, we looked at bandwidth, upper and lower frequencies, minus 3 dB points, and quality or Q factor. All these are terms used in designing and building of band pass filter, BPF, and indeed resonance circuit are used in 3-element mains filter designs to pass all frequencies within the passband angle while rejecting all others. However, the main aim of this tutorial is to analyze and understand the concept of how series resonance occurs in passive RLC series circuit. There was in RLC filter networks and designs is output the scope of the particular tutorial, and so will not be looked at here. For that, I'm so sorry. So in some future classes, I will explain that part also. For resonance to occur in any circuit, it must have at least one inductor and one capacitor. Please remember this part. Resonance is the result of the oscillations in a circuit as stored energy is passed from the inductor to the capacitor. And resonance occurs when XL equals to XC, and the imaginary part of the transfer function is 0. Yes. At resonance, the impedance of the circuit is equal to the resistance value as Z equals to R, because XL equals to XC. So that part will be vanished. So only R will be there. So Z is equals to R. No problem with this. At low frequencies, the series circuit is capacitive. That is, X is greater than XL. This gives the circuit a leading power factor. And then at high frequencies, the series circuit is inductive as XL greater than XC. This gives the circuit lagging power factor. These all are very important questions. Now, the high value of current at resonance produces very high value of voltage across inductor and capacitor. Series resonance circuits are useful for constructing highly frequency selective filters. However, its high current and very high component voltage values can cause damage to the circuit. And then the most prominent feature of the frequency response of a resonance circuit is a sharp resonant peak in its amplitude characteristics. You all know that already. Because impedance is minimum and circuit is and current is maximum, series resonance circuits are also called acceptor circuits. So very good information. And finally, with the help of this link, I developed the lecture and some few more books also helps me a lot. Thank you all for watching this lecture. Goodbye. Take care.